This lesson is on linear approximation. Now, we're going to take a look at the graph of this one so we can really get a good grasp on what is linear approximation, why do we use it. First word is linear. We're going to be looking at both the slope of the secant line and the slope of the tangent line. That will help you understand linear approximation. Approximate means they are close to each other, all right? The slope of the tangent line we learned is close to the slope of the secant line whenever x2 and x1 get really close to each other. So keep that in mind as we go through this lesson. Our first example is going to be approximate 1 over 10 minus 1 over 9.9. Now, before we get into this example, let's dive further into the linear approximation equation and why it works. So when we learned about instantaneous rate of change, we learned that it was actually just the limit of the slope of the secant line. For example, when x2 becomes x1, it becomes the slope of the tangent line. And we're going to take a look at the graph of this particular function we create and see exactly why that is. So let's just go to step 1. This is the hardest step for most students. You know, in order for linear approximation to work, you actually have to have a function. So notice what this question is asking. Approximate 1/10 minus 1 over 9.9. Notice how these two numbers are close to each other. Notice the format of our fractions. It's 1 over something. Okay, so this tells us, this will give us a hint as to what our function is going to be. Now again, going back to the formula, we can see kind of the format of linear approximation. The slope of the secant line is approximately equal to the slope of the tangent line whenever x2 becomes really close to x1. Given that information, we can deduce that this must be our x2 and this must be our x1. So x2 would be 10, x1 would be 9.9. This then would be f of x2, this would be f of x1. Okay? Putting that together, our function is just going to be 1 over x. Again, 1/10 and 1 over 9.9 would tell us that our function is 1 over x. As you do more of these examples, you get more comfortable with what the function is. Step 2 is to write out what is known. So now we know x2 is 10, x1 is 9.9, f of x2 is 1/10, f of x1 is 1 over 9.9. Next, this is the same formula you're going to use every single time for linear approximation. Now, notice how many variables are in this formula. This is one variable, the slope of the tangent line at x1. This is another variable, f of x2. F of x1 is another variable, x2 and x1. As long as you know 4 out of the 5, you can solve a linear approximation problem. Now, for this particular example, we're going to take a look at exactly what we're trying to solve for. Notice the question is asking for 1 over 10 minus 1 over 9.9 to approximate that, not to plug it into your calculator, but to approximating it using linear approximation. So this whole top of the fraction, let's see if I can underline it somehow, is actually what we're solving for. We just need to get that by itself for this particular example. Now, we need to find additional unknown values. We don't know f prime of x1, but we can figure it out because we know the original function is 1 over x. We can take the derivative of that and plug in x1, which is what we're going to do. So since f of x is 1 over x, we can rewrite that as x to the negative 1. We can use the power rule to find its derivative, which is going to be negative 1x to the negative 2, and then just plug in x1 to figure out the derivative at x1. So this also involves taking the derivative. Now since x1 is 9.9, we're going to take the derivative of 9.9 at 9.9, and we're going to get negative 0.0102. So that will give us that part of the equation formula that we need in order to isolate the top here or figure out what this change in f is. We already know what x2 minus x1 is, so we have everything we need except for the top here. Okay, so let's just plug in everything we know. We just figured out f prime of x1 over here on the left. We already know x2 and x1. We just need to figure out the change in f here. 1/10 minus 1 over 9.9. So it's tempting because we could just do a calculator, right? But the way linear approximation works is we're just going to isolate what's there on the right-hand side, get this by itself. And the slope of the tangent line will give us a good approximation here because these x values are so close to each other. We're going to take a look at the graph of this one to give some further comprehension. So step 6 is to isolate the expression being approximated, in this case 1/10 minus 1 over 9.9. Now sometimes with linear approximation, you could be solving for maybe x2 or x1, and you have to get those by themselves. We'll do some other examples like that later on. But for now, we're just going to get the top isolated, so I'm going to simplify the bottom to 0.1, and then now all we have to do is multiply both sides by 0.1, which is what we're going to do. So we get 0.1 times negative 0.0102 is approximately equal to what we're trying to approximate, which is namely 1/10 minus 1 over 9.9. And when we do this in our calculator, we get negative 0.00102. So this right here is going to give us a really close approximation to 1/10 minus 1 over 9.9 using the tangent line. So you might be saying, well, why did we do this? Why didn't we just plug into the calculator? Well, there are times when we can't actually find the actual answer. We have to use a linear approximation to solve. In fact, you can do that with a lot of different computations. Let's say you wanted to compute the 4th root of 7. Well, let's say you didn't have a calculator on hand, but you could use linear approximation to approximate that. Okay, or let's say you didn't have an algorithm, right, to solve for that. That's how you would possibly use linear approximation. So I do want to show you what the graph of this looks like. This is the graph of 1 over x, and I've plotted a point at 9 and plotted a point at 10. So notice the y value at 9 is 1/9, the y value at 10 is 0.1. So let's just say we wanted to, like we just figured out, we want to figure out what, basically the difference between f of 10 and f of 9. In other words, 1/10 minus 1/9. Well, right here, this purple line, we can look down here and see the slope of that line is negative 0.011. As I drag this point, so they're so close that if you drag this point on the point at 10 on top of the point at 9, you can see that the slope of the tangent line, whoops, I messed up there a little bit. Let's stop right there at point at 9. You can see that the instantaneous rate of change, don't want to see that, is, it's hard to stop there. Give me a second, now we'll stop it there. Okay, so here's what the tangent line looks like at 9, or f prime of x1. It's negative 0.1235 approximately. So we can see that the slope of this line is very close to the slope of the secant line from 9 to 10. And in fact, the closer, let's say we bring 10 closer to 9, we can see the slope of that secant line is going to be even closer to the slope of the tangent line at 9. That's all linear approximation is. It's just saying that the slope of the secant line gets really close to the slope of the tangent line as x2 approaches x1. All right, that's it for this example, approximating a value using linear approximation. If you have any other questions about it, let me know.